For more than a century, Einstein's theory of relativity has stood like a monument over modern physics. It explained gravity. It explained the motion of planets. It explained why time bends near massive objects and why light curves around stars. Again and again, the universe seemed to confirm him. Every test, every observation, every generation of scientists returning to the same conclusion. Einstein was right, but far beyond Earth, beyond the Milky Way, beyond the reach of any telescope humanity had ever built before. Something ancient was waiting in the dark, and when James Webb looked at it, astronomers froze. Because Webb did not just find distant galaxies, it found galaxies that seemed too bright, too massive, too structured, too old for the age of the universe they were supposed to belong to. Systems that looked like they had no business existing so soon after the Big Bang. Galaxies forming when the cosmos was still young, chaotic, and supposedly nowhere near ready to build structures like that. At first, scientists thought it had to be a mistake. A calibration problem, a redshift error, a processing artifact, something in the data, something in the model, something that would make the tension go away. But it didn't go away. The more Webb observed, the stranger the picture became. Objects appearing too early, black holes growing too fast, cosmic structure rising out of the primordial universe with an efficiency that made standard models look suddenly fragile. And this is where Einstein enters the story, because if the universe built massive structures earlier than expected, then either our understanding of cosmic evolution is missing something important, or gravity itself may not behave exactly the way we thought it did on the largest scales. That is not a small problem. That is the kind of problem that cracks open textbooks, the kind of problem that makes physicists argue late into the night, the kind of problem that forces a terrifying question into the room. What if Einstein was not completely wrong, but not completely right either? If you're fascinated by the secrets of the universe, subscribe now, because what you're about to hear might completely change how we understand reality. For over 100 years, relativity has been one of the greatest triumphs in human thought. Before Einstein, gravity was described by Isaac Newton as a force pulling objects together across space. It worked beautifully for apples, cannons, and planets. But there were cracks. Tiny ones. Mercury's orbit did not behave exactly the way Newton's equations said it should. Light itself seemed to have no clear place in the old picture of gravity. Then Einstein changed everything. He proposed that gravity was not really a force in the ordinary sense. It was geometry. Mass told spacetime how to curve, and curved spacetime told matter how to move. Planets were not being yanked through emptiness by invisible ropes. They were following the shape of a warped cosmic stage. That idea sounded almost absurd, until it started winning. Relativity explained Mercury. It predicted gravitational lensing, where light bends around massive objects. It predicted time dilation, which has to be corrected for every day in GPS satellites. It predicted black holes long before anyone had seen evidence for them. Later, it predicted gravitational waves, ripples in space-time itself, and a century after Einstein proposed them, detectors on Earth finally caught them passing through the planet. Again and again, relativity survived. So when scientists built models of the universe itself, Einstein was there too. His equations became the backbone of cosmology. They helped describe the expansion of the universe, the growth of galaxies, the behavior of matter on the largest scales humanity could imagine, even when the math led to strange additions like dark matter and dark energy. The deeper structure still belonged to Einstein, which is exactly why Webb's discoveries hit so hard, because when the most successful theory in modern physics meets observations that do not comfortably fit, one of two things is happening. Either the universe is hiding something, or our understanding of it is. Astronomers knew the early universe was supposed to be chaotic. After the Big Bang, the universe was a hot, dense fog of particles and radiation. For hundreds of millions of years, matter slowly cooled. Gravity gradually pulled gas together. The first stars ignited. Then clusters formed. Then galaxies. At least, that's how the story was supposed to unfold, according to the standard cosmological model, built from Albert Einstein's equations of gravity and decades of astronomical observations. Large galaxies should take time to assemble. A lot of time. The early universe was messy, violent, turbulent. Stars had to form first, then groups of stars, then small proto-galaxies, then collisions and mergers slowly built the large galaxies we see today. It was supposed to be a gradual construction project spanning billions of years, and until recently, every telescope we had seemed to support that timeline. But then a new eye opened in space. In December 2021, humanity launched the most powerful space observatory ever built, the James Webb Space Telescope. Webb was designed to look deeper into the universe than any telescope before it, and looking deeper into space means looking further back in time, because light does not travel instantly. When we see a galaxy billions of light years away, we are not seeing it as it is today. We're seeing it as it was billions of years ago. The light left that galaxy long before Earth even existed, so when Webb began staring into the deep universe, astronomers expected something extraordinary. But they did not expect this. Almost immediately after the first deep field observations came back, researchers started noticing objects that didn't seem to belong in the early universe. Bright galaxies, massive galaxies, structured galaxies, galaxies that looked mature, and they were appearing at distances that meant they existed only 300 to 500 million years after the Big Bang. To put that in perspective, the universe today is about 13.8 billion years old. These galaxies were showing up when the universe was barely 3% of its current age. And that's when things started getting uncomfortable, because the model said something very different. According to simulations based on Einstein's equations and the standard cosmological framework, galaxies at that early time should have been small, faint and chaotic, tiny clumps of stars just beginning to assemble, not massive cosmic cities blazing with billions of stars. Yet that is exactly what Webb seemed to be seeing. At first, many astronomers assumed the data must be misleading. Distance measurements in cosmology rely heavily on something called redshift, a stretching of light as the universe expands. If the redshift estimate is wrong, the inferred distance could also be wrong. Maybe the galaxies were closer than they appeared. Maybe dust or unusual stellar populations were confusing the measurements. Maybe the brightness was being misinterpreted. But then more data arrived, and the pattern didn't disappear. If anything, it grew stronger. Multiple research teams analyzing Webb observations began reporting the same strange result. Early galaxies appeared far more massive and evolved than theoretical models predicted. Some estimates suggested stellar masses approaching 10 billion solar masses. That's enormous. For comparison, the Milky Way contains about 60 billion solar masses in stars, and it has had over 13 billion years to build itself. Yet Webb was seeing galaxies not dramatically smaller than that, forming when the universe had barely begun. And that's when scientists started whispering something they rarely say out loud. Something didn't add up. Because if galaxies were assembling this quickly, then gravity was doing something unexpected. Or the early universe behaved very differently than our models assumed. And if that were true, then the equations that describe the large-scale behavior of gravity, equations rooted in Einstein's theory of general relativity, might be incomplete. Not necessarily wrong, but incomplete. And that possibility opened a door to one of the deepest scientific debates happening right now. Because if gravity behaves differently across cosmic scales, then the entire story of how the universe formed could change. But before we go further, we need to understand exactly how surprising Webb's discovery really is. Because the tension between theory and observation didn't appear suddenly. For years, small cracks had already been forming, and Webb may have just widened them. For decades before the James Webb Space Telescope ever unfolded its golden mirrors in space, cosmologists believed they had a reasonably clear picture of how the universe grew up. Not perfect, but stable. The backbone of that picture is something called the Lambda-CDM model. It's the standard model of the universe. Lambda represents dark energy. CDM represents cold dark matter. Together, they describe how matter and energy shape the cosmos. In this model, gravity slowly gathers matter into structures. Tiny fluctuations in the early universe grow over time. Clouds of gas collapse. Stars ignite. Galaxies assemble. But this process takes time. A lot of time. In the early universe, gravity was working with very little raw material. Matter had only just begun clumping together after the universe cooled enough for atoms to form. Astronomers believe the first galaxies should have been small, messy, primitive, the cosmic equivalent of construction sites. Over billions of years, those small systems merged, collided, and accumulated mass until they became the giant galaxies we see today. That timeline matched observations from earlier telescopes, especially the legendary Hubble Space Telescope. Hubble could see galaxies billions of years into the past, and what it saw mostly matched expectations. The deeper it looked into the past, the smaller and more chaotic galaxies appeared. It was like watching cosmic evolution in reverse. Modern galaxies, then earlier ones, then smaller ones, then faint proto-galaxies. The pattern made sense. Until Webb arrived, because Webb sees something Hubble couldn't, infrared light, and that changes everything. As the universe expands, light traveling through it stretches. This stretching shifts light toward the red end of the spectrum. The farther away something is, the more its light is stretched. This effect is called cosmological redshift. The earliest galaxies are so distant that most of their light has shifted into infrared wavelengths. Hubble could barely detect that. Webb was designed specifically for it. So when Webb turned its infrared eyes toward the deepest parts of the universe, astronomers were effectively opening a new time machine. They were about to see farther back than ever before, and almost immediately, strange signals started appearing. At first, they looked like faint smudges in Webb's earliest deep field images, but when scientists analyzed the data carefully, those smudges resolved into galaxies, very distant galaxies. Galaxies with redshift values suggesting they existed just 200 to 400 million years after the Big Bang. That alone would have been exciting, but the real shock came when astronomers estimated their brightness and mass. Because brightness in astronomy tells you something important. It tells you how many stars are there, and the numbers Webb was returning were unsettling. Some of these galaxies appeared to contain billions of stars, which raises an immediate problem. Stars take time to form. Gas clouds collapse slowly under gravity. Stars ignite. They live. They explode. They enrich surrounding gas with heavier elements. Then new generations of stars form from that enriched material. Each step requires time. But Webb's galaxies looked like they had skipped several steps. They appeared mature, structured, complex. Too complex. It was as if astronomers had expected to find toddlers, but instead discovered fully grown adults. And that's when the phrase started circulating through astrophysics departments around the world. These galaxies shouldn't exist yet. Now, scientists are careful with language. No one was saying Einstein had suddenly been proven wrong overnight. But the observations created a tension, because when observations contradict models, something has to give. Either the data is wrong, the interpretation is wrong, or the model is incomplete. For months, researchers examined the possibility that the distances were miscalculated. Maybe the redshift estimates were off. Maybe the galaxies weren't actually that far away. But spectroscopic follow-up observations confirmed several of the extreme cases. These galaxies really were that distant, which meant they really were that early, and really that massive. And suddenly, a quiet question started echoing across cosmology. How did gravity build these structures so fast? Because according to the mathematics derived from Albert Einstein's equations, structure formation simply shouldn't happen that quickly. Gravity pulls matter together, but the rate of growth is limited. It takes time for tiny density fluctuations to evolve into massive galaxies. If galaxies were already enormous only a few 100 million years after the Big Bang, then either matter clumped faster than expected, or something boosted the gravitational process, or something else entirely is missing from the picture. And that possibility opened the door to one of the most fascinating debates in modern astrophysics, because the tension wasn't coming from just one discovery. It was coming from several. Webb wasn't just finding early galaxies, it was also detecting signs of supermassive black holes forming incredibly early in cosmic history. Some of these black holes appear to have masses equivalent to millions or even billions of suns, and they seem to exist in galaxies that themselves are extremely young, which creates another puzzle. Black holes grow by consuming matter, but even under ideal conditions, growth takes time. Yet Webb's observations suggest that some black holes reached enormous sizes far sooner than theoretical models predicted. And when multiple cosmic puzzles start appearing at the same time, scientists begin to wonder whether the problem runs deeper. Because gravity controls everything in cosmology: galaxy formation, black hole growth, large-scale cosmic structure. If gravity behaves slightly differently under extreme cosmic conditions, then the entire history of the universe could unfold differently than expected. Which brings us back to Einstein, because Einstein's theory of general relativity is the mathematical framework used to describe gravity across the cosmos. It has passed every experimental test humans have thrown at it, from gravitational waves to black hole imaging. But most of those tests happen on relatively small scales, inside galaxies, around stars, near black holes. The largest scales of the universe are harder to test. And Webb may now be giving us the first real hints that something about those scales might behave differently than expected. But before scientists rewrite the laws of physics, they have to explore every other possibility first. And that's exactly what they're doing, because there are several potential explanations for Webb's mysterious galaxies. Some of them preserve Einstein completely. Others suggest entirely new physics, and one of those possibilities involves something that has been haunting cosmology for decades: dark matter. For nearly a century, astronomers have known that most of the universe is invisible, not metaphorically invisible, literally invisible. When scientists measure how galaxies rotate, they discover something strange. The outer stars in galaxies move far faster than they should if only visible matter were present. According to Newtonian gravity and even general relativity, those stars should be flung away into space. But they aren't. Something unseen is holding galaxies together. That unseen component is called dark matter. Scientists believe dark matter makes up roughly 85% of all matter in the universe. That means everything we can see, stars, planets, gas, galaxies, people, represents only a tiny fraction of what actually exists. Dark matter does not emit light. It does not absorb light. It barely interacts with ordinary matter at all. But it has gravity, and gravity leaves fingerprints. By observing how galaxies move and how light bends around massive structures, an effect known as gravitational lensing, astronomers can map where dark matter must be located. Those maps reveal enormous invisible halos surrounding galaxies. In fact, galaxies appear to form inside dark matter halos. The dark matter gathers first, then ordinary gas falls into the gravitational wells it creates. Stars ignite. Galaxies form. This idea became a cornerstone of modern cosmology, because without dark matter, galaxies shouldn't exist the way they do. So when astronomers build simulations of the early universe, dark matter plays a critical role. The process is supposed to unfold like this. Shortly after the Big Bang, tiny fluctuations in density existed throughout space. Some regions contained slightly more matter than others. Gravity amplified those differences. Dark matter began clumping together. Those clumps formed a scaffolding of cosmic structure. Then gas collapsed into those scaffolds. Stars formed. Galaxies slowly emerged. But here's the key word: slowly. The simulations show that early galaxies should be relatively small because there hasn't been enough time for massive dark matter halos to grow. Which brings us back to the problem Webb revealed, because the galaxies it's seeing appear far more massive than those simulations predict. That suggests something unexpected happened in the early universe. Either galaxies formed stars much faster than we thought, or dark matter collapsed into large structures far more quickly. Both possibilities challenge existing models, and neither explanation is simple, because the rate at which dark matter clumps together is controlled by fundamental physics. It depends on the nature of dark matter particles, their speed, their interactions, their temperature in the early universe. That's why the current model uses the term cold dark matter. Cold doesn't mean temperature in the everyday sense. It means the particles move relatively slowly. Slow particles clump efficiently. Fast particles smear out structure. Cold dark matter allows galaxies to form, but Webb's observations may suggest that something different happened. Maybe dark matter clumped faster than predicted, or maybe galaxies converted gas into stars with extraordinary efficiency. That some researchers have raised an even more radical possibility. What if dark matter behaves differently than expected? Because despite decades of experiments, scientists still do not know what dark matter actually is. It could be exotic particles never observed in laboratories. It could interact through forces we don't yet understand. Or, in a more controversial idea, dark matter might not exist at all. Instead, gravity itself might behave differently on cosmic scales. That idea leads to something physicists call modified gravity. The concept is simple. If Einstein's equations are slightly incomplete, gravity might become stronger or weaker at extremely large distances. That change could alter how galaxies form. In some modified gravity theories, structures in the universe could grow faster than predicted by standard cosmology, which might explain why Webb sees large galaxies so early. But proposing modifications to Einstein's theory is not something scientists do lightly. Relativity has passed countless tests. It predicted black holes. It predicted gravitational waves. It predicted time dilation. Modern technology like GPS literally depends on it. So abandoning Einstein would require overwhelming evidence. And right now, Webb's discoveries are intriguing, but not yet definitive. Many astronomers believe the answer may lie somewhere in between. Maybe the galaxies are not quite as massive as initial estimates suggested. Maybe star formation in the early universe was far more efficient than models assumed. Or maybe the earliest galaxies contained unusually bright populations of massive stars. Stars that burned hot and blue, making galaxies appear more luminous than their mass would normally allow. Each possibility is being explored. New Webb observations are arriving constantly. Spectroscopic measurements are refining galaxy distances. Simulations are being updated, but something about the early universe still feels strange. Because the Webb discoveries are not isolated, they connect to another major puzzle in cosmology, a puzzle that has been quietly growing for years. It's called the expansion rate crisis, and it may hint that our understanding of the universe is missing something fundamental. For nearly a century, astronomers have known that the universe is expanding. That discovery came in the 1920s, when the American astronomer Edwin Hubble noticed something extraordinary. Distant galaxies were moving away from us, and not randomly. The farther away a galaxy was, the faster it appeared to recede. It was as if space itself was stretching. This relationship became known as the Hubble-Lemaitre law. The implication was revolutionary. The universe was not static, it was growing, and if you run that expansion backward in time, everything converges toward a single hot, dense beginning, what we now call the Big Bang. For decades, cosmologists have been trying to measure exactly how fast the universe is expanding. That rate is known as the Hubble constant, and measuring it turns out to be incredibly difficult because the universe is vast, and cosmic distances are notoriously tricky. To solve the problem, astronomers developed multiple methods. One approach measures nearby galaxies and calculates distances using objects called standard candles. The most famous of these are Cepheid variables, stars whose brightness fluctuates in a predictable way. By measuring their pulsation period, astronomers can determine their true luminosity, and then they compare it to how bright the star appears from Earth. That reveals the distance. Using this method, researchers have built a ladder of distance measurements stretching deep into space. But there is another completely different way to measure the expansion of the universe. Instead of looking at nearby galaxies, scientists study the oldest light in existence, the faint afterglow of the Big Bang itself. This radiation is called the cosmic microwave background. It was first detected in 1965 and later mapped with extraordinary precision by missions like Planck Space Observatory. The microwave background carries a snapshot of the universe when it was just 380,000 years old. By analyzing tiny fluctuations in that radiation, scientists can infer the physical properties of the early cosmos, including how fast the universe should be expanding today. For a long time, astronomers assumed these two methods would agree. After all, they are measuring the same universe, just from different angles. But over the past decade, something strange has emerged. The two measurements don't match, not even close. The expansion rate calculated from nearby galaxies appears significantly faster than the expansion rate inferred from the cosmic microwave background. This discrepancy is now known as the Hubble tension, and it has become one of the biggest unsolved mysteries in cosmology, because if both measurements are correct, then something about our model of the universe is wrong. And here's where Webb enters the story again. The James Webb Space Telescope is now helping astronomers remeasure cosmic distances with unprecedented accuracy. Webb can observe Cepheid stars in distant galaxies far more clearly than earlier telescopes, which allows scientists to refine the distance ladder. In recent observations, Webb confirmed something unsettling. The earlier measurements from the Hubble Space Telescope were largely correct. The faster expansion rate appears real. That means the discrepancy is not simply a measurement error. Something deeper may be happening. If the universe is expanding faster today than predicted by early universe physics, then the ingredients in our cosmological model may be incomplete. Some scientists suspect dark energy might evolve over time. Others propose exotic particles that existed in the early universe but vanished later, and some researchers wonder whether the mathematics derived from Albert Einstein's theory of gravity might need modification at cosmic scales. It's important to understand what that means. No one is claiming relativity is wrong in everyday conditions. The theory has been tested around stars, black holes, and even gravitational waves, but cosmology operates at scales billions of light years across. Scales where new physics might emerge, and if gravity behaves slightly differently across those distances, then the growth of galaxies, the expansion of space, and the structure of the universe could all change, which would bring us right back to Webb's early galaxy discoveries. Because if the universe expanded differently in its earliest epochs, then galaxies might have formed faster than predicted, and the pieces of the puzzle might begin to align. But this is where the story becomes even stranger, because Webb has uncovered another cosmic mystery that might connect to all of this, something about the shape of the universe itself. And what astronomers are seeing could hint that the large-scale structure of the cosmos is far more complicated than we imagined. When astronomers talk about the shape of the universe, they are not talking about something you could step outside and look at. The universe has no outside. Instead, scientists are describing how space itself behaves on the largest possible scales. Is it flat? Is it curved? Is it finite or infinite? These questions sit at the heart of modern cosmology, and they trace directly back to the equations written by Albert Einstein more than a century ago. Einstein's theory of general relativity does something remarkable. It links gravity to the geometry of space and time. Mass and energy bend space-time, and that bending determines how objects move. When cosmologists applied those equations to the entire universe, they discovered something profound. The universe could have three possible geometries. It could be closed, like the surface of a sphere. It could be open, like a saddle. Or it could be perfectly flat. For decades, astronomers have been trying to determine which of those possibilities describes our cosmos. And the answer, according to the best observations we have, is astonishing. The universe appears to be almost perfectly flat. Measurements from the Planck Space Observatory, studying the cosmic microwave background, show that the geometry of space is extremely close to flat, so close that even the tiniest deviation would change the fate of the universe. Flat geometry means the universe can expand forever. Gravity slows expansion slightly, but not enough to reverse it. Dark energy then accelerates the expansion, and galaxies drift farther and farther apart. But Webb's discoveries have made some scientists revisit a deeper question. If galaxies formed earlier than expected, if black holes appeared faster than predicted, if the expansion rate seems inconsistent depending on how you measure it, then maybe something about our assumptions regarding the large-scale structure of the universe is incomplete, because there is another layer to the cosmic story, one that goes beyond individual galaxies. Astronomers have discovered that galaxies are not scattered randomly through space. They form enormous patterns, filaments stretching across hundreds of millions of light years, clusters of galaxies gathered like islands, vast empty regions called cosmic voids. This enormous network is known as the cosmic web. It is the largest structure in existence, and according to the standard cosmological model, the cosmic web emerged slowly as gravity amplified tiny density fluctuations left over from the Big Bang. Dark matter formed the skeleton. Gas followed. Galaxies grew along the filaments. The entire structure evolved over billions of years, but Webb's observations suggest that large-scale organization may have begun earlier than expected. Some of the galaxies being observed appear to exist inside surprisingly developed environments. which raises a subtle but important question. What if the early universe wasn't as uniform as we thought? Because the standard cosmological model assumes something called cosmic homogeneity. On very large scales, the universe should look roughly the same in every direction. No preferred regions, no special locations, but if large structures formed unusually early, that assumption may require refinement, and if homogeneity breaks down at certain scales, then the gravitational evolution of the universe might be more complex than our simplified models assume. But that is only one piece of the puzzle, because Webb has also been revealing something else about the early universe, something about the first generation of stars. And these stars may have been unlike anything that exists today. Astronomers call them population 3 stars. These were the very first stars ever born. They formed from primordial gas composed almost entirely of hydrogen and helium. No heavy elements, no metals, just the simplest ingredients created in the Big Bang. Without heavier elements to cool collapsing gas clouds efficiently, these early stars may have grown to enormous sizes, hundreds of times the mass of the Sun, perhaps even more. And massive stars burn incredibly hot and bright. If early galaxies were filled with these enormous stars, they would appear far brighter than expected for their mass, which could partially explain Webb's surprising observations. Galaxies might not actually be as massive as they appear. They might simply contain unusually luminous stars. That possibility is currently being investigated using Webb's powerful spectroscopic instruments. But even if population 3 stars account for some of the brightness, they may not explain everything, because Webb is also detecting chemical signatures in some early galaxies suggesting that multiple generations of stars have already lived and died, which implies a surprisingly rapid cycle of star formation and enrichment. And that again brings us back to the same uncomfortable conclusion. Something about the early universe evolved faster than predicted. And when cosmic evolution happens faster than expected, gravity is usually involved, which brings scientists back once again to Einstein. But here's the fascinating part. Even if Webb's discoveries eventually reveal that Einstein's theory needs refinement, that would not diminish his achievement. In fact, it would confirm something Einstein himself once said: no theory is ever final. Science is a process. Each discovery reveals deeper layers of reality. And sometimes the universe surprises us in ways that force us to rethink even our most trusted ideas. Right now, Webb is doing exactly that. It is opening a new window into the earliest chapters of cosmic history. And what we are seeing through that window is both thrilling and unsettling, because every new observation seems to raise another question. How did the first galaxies form so quickly? Why do some early black holes appear impossibly large? Why does the expansion rate of the universe refuse to agree with itself? And perhaps most importantly, what else is waiting to be discovered in the darkness beyond Webb's deepest images? Because the deeper we look into space, the closer we get to the moment the universe began. And the closer we get to the limits of everything we thought we knew. For decades, astronomers believed they had a clear timeline for the birth of the first stars. After the Big Bang, the universe was a hot plasma of particles and radiation. Eventually, it cooled enough for protons and electrons to combine into hydrogen atoms. This moment, called recombination, occurred about 380,000 years after the beginning. The universe then entered a long quiet period. Astronomers call it the cosmic dark ages. During this time there were no stars, no galaxies, just vast clouds of hydrogen gas slowly drifting through darkness. Gravity was at work, but very gradually. Tiny fluctuations in matter density, remnants of quantum ripples in the early universe, slowly grew under gravitational attraction. Gas began collapsing into the first dense regions, and eventually, somewhere in that darkness, the first stars ignited. These first stars are believed to have appeared roughly 100 to 200 million years after the Big Bang. They were not ordinary stars, they were monsters. Astronomers refer to them as population 3 stars. Unlike modern stars, they formed in a universe with almost no heavy elements. The gas contained mostly hydrogen and helium. Without heavier elements to help radiate energy away, collapsing gas clouds heated up more easily. That allowed the first stars to grow incredibly massive. Some theoretical models predict masses 100 to 300 times larger than the Sun. Stars like that burn extremely hot. They shine intensely. but they also live very short lives. Within a few million years, many of them exploded as powerful supernovae. Those explosions scattered heavy elements, carbon, oxygen, iron, into surrounding space. This process changed everything, because heavy elements make it easier for gas to cool and fragment, which allows smaller stars to form. So after the first generation of massive stars died, the next generation of stars could form more easily. Galaxies slowly assembled. Over hundreds of millions of years, the universe transitioned from darkness to light. This era is known as the epoch of reionization. Radiation from the first stars and galaxies began ionizing the hydrogen fog that filled the cosmos. Gradually, the universe became transparent to ultraviolet light. By about 1 billion years after the Big Bang, the modern cosmic era had begun. That is the traditional picture. A slow emergence of structure, darkness giving way to light, stars forming gradually, galaxies growing step by step. But Webb's observations suggest that parts of this timeline may have unfolded far faster. When the James Webb Space Telescope examines extremely distant galaxies, it is essentially observing the universe during that transition from darkness to light. And some of the galaxies it sees already appear surprisingly developed. They show evidence of multiple stellar generations. That means star formation and supernova explosions may have happened extremely rapidly, within just a few 100 million years. Which again raises the same fundamental question: how did the universe build complexity so quickly? One possibility involves something called starburst galaxies. These are galaxies that form stars at extraordinary rates, hundreds or even thousands of times faster than the Milky Way. If early galaxies experienced intense bursts of star formation, they could accumulate large stellar populations in a short time. But even that explanation has limits. Gas supply must be enormous. Gravity must pull matter inward efficiently. Feedback from supernova explosions must not disrupt the process too quickly. Models suggest such extreme star formation could occur, but sustaining it long enough to produce massive galaxies so early remains difficult. Another possibility is that the earliest galaxies grew through extremely rapid mergers. In the dense early universe, galaxies were much closer together. Collisions would have been common. Two small galaxies merge, then merge again and again. Each merger adds mass. Each merger triggers star formation. Over time, galaxies grow larger. This hierarchical merging is already part of standard cosmology. But Webb's discoveries may suggest the process began earlier than expected, which again circles back to the central mystery. Something in the early universe may have accelerated structure formation. Perhaps the initial density fluctuations were larger than predicted. Perhaps dark matter clumped more efficiently. Perhaps star formation physics behaved differently in primordial environments. Or perhaps there is something deeper happening, because Webb has revealed yet another phenomenon that may connect to these puzzles. Something involving the earliest supermassive black holes and the existence of these ancient monsters may be one of the most difficult problems in modern astrophysics. There is something deeply unsettling about black holes, not just because they trap light, but because of how quickly some of them seem to grow. At the center of almost every large galaxy sits a supermassive black hole, including the one at the heart of our own galaxy, the Sagittarius A. These objects are not ordinary black holes. They contain millions or billions of times the mass of the Sun. And for decades, astronomers have struggled to explain how they formed, because black holes grow by consuming matter. Gas falls inward, stars are torn apart, material spirals into an accretion disk. Over time, the black hole gains mass. But this growth has limits. Radiation from the accretion disk pushes outward, slowing the inflow of matter. This creates what astrophysicists call the Eddington limit, a natural cap on how quickly a black hole can grow. Even under ideal conditions, building a billion solar mass black hole should take hundreds of millions of years, possibly longer. Yet observations keep revealing enormous black holes that appear extremely early in cosmic history. Some quasars, intensely luminous galaxies powered by feeding black holes, already existed when the universe was less than 1 billion years old. Astronomers have been puzzling over these objects for years, but the James Webb Space Telescope is now pushing the mystery even further back in time. Webb has detected signs of growing black holes in galaxies. only a few 100 million years after the Big Bang. Which raises a troubling possibility. If these black holes already existed that early, then they must have started forming extremely soon after the first stars appeared, possibly even earlier. And that creates a cosmic puzzle, because according to the equations derived from Albert Einstein's theory of general relativity, black holes form when massive stars collapse, but even the largest stars cannot produce black holes with billions of solar masses directly. They start small, then grow gradually. So how did the early universe produce such enormous objects so quickly? Scientists have proposed several ideas. One possibility is that the first stars were much larger than we expect. If early population third stars reached hundreds of solar masses, their collapse might produce relatively massive black hole seeds. Those seeds could then grow through rapid accretion, but calculations show that even this process struggles to explain the largest early quasars. Another hypothesis suggests that black holes may have formed directly from collapsing gas clouds, instead of forming stars first. Enormous gas clouds might have collapsed under gravity and formed black holes directly. These are known as direct collapse black holes. Such objects could begin life already containing 100,000 solar masses. From there, growth to supermassive scale becomes easier. But direct collapse requires very specific conditions. The gas must remain hot enough to avoid fragmenting into stars. Radiation must suppress cooling. The environment must be extremely dense. Whether such conditions existed widely enough in the early universe is still debated. And then there is an even more radical possibility. What if some black holes formed before stars even existed? Physicists have theorized the existence of primordial black holes. These objects would not originate from collapsing stars at all. Instead, they could form from density fluctuations in the extremely early universe, fractions of a second after the Big Bang. If primordial black holes existed, they could act as seeds for later supermassive black holes. They might grow over billions of years into the enormous objects we observe today. This idea is fascinating because it connects black hole formation directly to the physics of the early universe. But evidence for primordial black holes remains uncertain. Some observations hint at their existence. Others place limits on how common they could be. The debate continues, but Webb's discoveries are forcing scientists to confront the possibility that black hole growth in the early universe was far more efficient than our models predicted. And if that's true, then gravity may have behaved differently under those conditions. Perhaps matter collapsed faster. Perhaps gas flowed inward more easily. Perhaps black holes consumed matter at rates exceeding the traditional Eddington limit. Or perhaps something about the structure of space-time itself allowed faster growth. Each possibility pushes researchers deeper into the unknown. Because black holes are not just astrophysical curiosities, they are laboratories for testing the laws of physics, the most extreme environments in the universe. Regions where gravity becomes so strong that space-time bends dramatically. And if anything in the cosmos has the potential to reveal cracks in Einstein's theory, it would likely be found there. But the deeper Webb looks into the early universe, the more it becomes clear that black holes are not the only things appearing sooner than expected, because the structure of entire galaxies may also be evolving in surprising ways. And the implications of that could reshape our understanding of how the cosmos built itself. For most of the 20th century, astronomers believed galaxies followed a fairly predictable evolutionary path. Small systems formed first. Then they merged. Over time, they grew into the large spiral and elliptical galaxies we see today. That idea became one of the central pillars of modern cosmology. It fits beautifully with simulations based on the Lambda-CDM model. In those simulations, the early universe looks like a chaotic landscape of tiny galaxies. They collide. They merge. Gravity pulls them together again and again. Over billions of years, the process builds the enormous galaxies we observe today. And when astronomers looked at distant galaxies through earlier telescopes like the Hubble Space Telescope, the images seemed to confirm this picture. The farther back in time we looked, the smaller and messier galaxies appeared. It was exactly what the models predicted. But when the James Webb Space Telescope began delivering its first deep observations, astronomers noticed something unexpected. Some early galaxies looked organized. Not chaotic, not distorted, but structured. In several cases, Webb has detected galaxies that appear to contain rotating disks. In other words, galaxies that resemble mature spiral systems, the kind of galaxies we normally associate with billions of years of evolution. Seeing such structures so early in cosmic history is surprising, because disk galaxies require stability. Gas must settle into rotational equilibrium. Stars must orbit in relatively ordered paths. Disturbances from mergers must be minimal. In the turbulent early universe, that kind of calm structure should be rare. Yet Webb appears to be seeing it. And that raises another fascinating possibility. Maybe galaxies sometimes form more smoothly than we expected. Instead of assembling purely through violent mergers, some galaxies might grow through a steady inflow of gas along cosmic filaments. These filaments belong to the cosmic web, vast strands of dark matter and gas stretching across the universe. Simulations show that gas can stream along these filaments into young galaxies. If the inflow is steady enough, it could allow rotating disks to form earlier than predicted. That idea has gained attention in recent years, but Webb's observations are pushing it into new territory. Because if disk galaxies existed only a few 100 million years after the Big Bang, then the conditions allowing stable rotation must have emerged extremely quickly, which again leads back to the same central mystery. How did the universe organize itself so fast? Gravity is the primary architect of cosmic structure. It pulls matter together. It shapes galaxies. It governs the motion of stars. And the equations describing gravity on cosmic scales ultimately come from Albert Einstein's theory of general relativity. But relativity does not act alone in cosmology. It operates within a framework that also includes dark matter and dark energy. And that framework may still be incomplete. Some physicists believe the solution may lie in a deeper understanding of dark matter. Perhaps dark matter particles interact in subtle ways that change how structures grow. Perhaps there are multiple types of dark matter. Or perhaps dark matter behaves differently at extremely high densities. Others suggest the answer might involve early dark energy, a temporary burst of energy in the early universe that altered the expansion rate and accelerated structure formation. This idea has gained attention partly because it could also help resolve the Hubble tension, the disagreement between different measurements of the universe's expansion. Still others are exploring modifications to gravity itself. Theories like MUND, modified Newtonian dynamics, and various extensions of general relativity attempt to explain galaxy behavior without relying on dark matter. Most of these models face serious challenges, but Webb's discoveries are encouraging scientists to re-examine every possibility. Because when observations challenge theory, science advances. That tension is where breakthroughs happen. And Webb is still only beginning its mission. The telescope is expected to operate for at least a decade, possibly longer. Every new observation pushes deeper into the past. Every new dataset adds pieces to the cosmic puzzle. And already, Webb is revealing details about the early universe that were completely invisible before. But perhaps the most important lesson from Webb's discoveries is not that Einstein might be wrong. It is that the universe is more complicated than we imagined. Einstein himself understood that. He once said, "The important thing is not to stop questioning." Science thrives on uncertainty. Every mystery is an invitation to look deeper. And the early universe is still full of mysteries, because the closer we get to the beginning, the stranger the cosmos appears. There is a moment in every scientific discovery when curiosity turns into something else. Concern. Not panic, not disbelief, but a quiet recognition that something fundamental might be missing. Astronomers studying the early universe are reaching that moment now, because the deeper the James Webb Space Telescope looks, the more often it encounters objects that seem just a little too mature for their age. A galaxy that appears too bright, a black hole that appears too large, a structure that appears too organized. Individually, any one of these discoveries could be explained away. But together they form a pattern, and patterns are what scientists pay attention to. To understand why this matters, we have to return to the fundamental blueprint of the universe. Cosmologists believe the large-scale structure of the cosmos emerged from tiny fluctuations that existed shortly after the Big Bang. These fluctuations are visible today in the faint variations of temperature across the cosmic microwave background. When the Planck Space Observatory mapped this ancient radiation with extraordinary precision, It revealed a pattern of hot and cold spots across the sky. Those spots correspond to regions where matter was slightly more or less dense. Over billions of years, gravity amplified those differences. Dense regions became galaxies and clusters. Less dense regions became cosmic voids. In other words, the universe's entire architecture was seeded by those tiny primordial fluctuations. And here is where things become intriguing. The size of those fluctuations determines how quickly structures can grow. If the fluctuations were slightly larger than predicted, gravity would have had a stronger starting point. Structures could form earlier. Galaxies could grow faster. Black holes could emerge sooner. In fact, some cosmologists are now re-examining the possibility that the early universe contained subtle variations in its density spectrum that we have not fully accounted for, because the Lambda-CDM model assumes a very specific pattern of fluctuations. That assumption fits most observations remarkably well, but Webb's discoveries are encouraging researchers to test whether small deviations might exist. Even tiny changes in the initial conditions of the universe could ripple forward across billions of years of cosmic evolution. Another possibility involves the physics of gas cooling and star formation. In the early universe, the chemistry of gas clouds was extremely simple. Hydrogen and helium dominated, yet some processes may have allowed gas to cool faster than expected. For example, molecular hydrogen can form under certain conditions and act as an efficient coolant. If this process occurred more frequently than models assume, early star formation could accelerate. More stars would form earlier. Galaxies would appear brighter and more mature. There is also the possibility that the early universe was more turbulent than we think. Shock waves from early supernova explosions may have triggered rapid star formation in nearby regions. Massive stars could have formed in clusters. These clusters might merge quickly, building larger stellar systems in a short time. But even with these mechanisms, some observations remain difficult to explain, as why some physicists are exploring deeper theoretical territory. Ideas involving early dark energy, interacting dark matter, or even modifications to the equations derived from Albert Einstein's theory of general relativity. None of these proposals are confirmed, but they represent something important. Science in motion, because history shows that when observations challenge established theories, extraordinary breakthroughs sometimes follow. In the early 20th century, astronomers believed the Milky Way was the entire universe. Then Edwin Hubble showed that distant galaxies existed far beyond it. Suddenly, the universe became vastly larger. Later, the discovery of cosmic expansion transformed our understanding again. Then the detection of dark matter, then dark energy. Each discovery revealed that the cosmos was more complex than expected. Webb may be continuing that tradition. It is allowing humanity to observe the universe at a level of detail that previous generations could barely imagine. Every deep field image contains thousands of galaxies. Some are so distant that their light has traveled for more than 13 billion years. That means the photons striking Webb's detectors began their journey when the first galaxies were forming, when the universe was still young, when cosmic history was just beginning. And hidden within those ancient beams of light may be clues about the fundamental laws governing the universe, clues that could refine our understanding of gravity, matter, and cosmic evolution, or perhaps confirm that Einstein's theory remains astonishingly accurate even at the largest scales. Either way, the investigation has only just begun. Because Webb is not just observing the universe, it is rewriting the timeline of cosmic history. For most people, the universe feels stable, the stars appear fixed, the night sky seems eternal. But the deeper scientists look, the more they discover that the cosmos is not calm at all. It is evolving, constantly. Galaxies collide, black holes merge, stars are born and die, and the fabric of space itself stretches across billions of light years. Understanding that evolution requires a mathematical framework. For more than a century, that framework has been general relativity, developed by Albert Einstein in 1915. Einstein's equations describe how mass and energy shape spacetime. They predict how planets orbit stars. They explain why light bends around massive objects. They even predicted the existence of black holes long before astronomers found evidence for them. Time and again, experiments have confirmed Einstein's predictions with extraordinary precision. Gravitational waves detected by observatories like LIGO Scientific Collaboration match the theory perfectly. the first image of a black hole captured by the Event Horizon Telescope collaboration, also agreed with Einstein's equations. Even technologies used every day on Earth rely on relativity. The satellites that power GPS must account for time dilation predicted by Einstein. Without those corrections, navigation systems would drift kilometers off course. In other words, relativity works extremely well. But science has learned an important lesson over the centuries. Even the most successful theories eventually face limits. Newton's laws of motion worked perfectly for centuries. They describe everyday physics beautifully. But when scientists began studying objects moving near the speed of light, Newton's equations broke down. Einstein's relativity replaced them in those extreme regimes, and now physicists wonder whether relativity itself might one day require an extension. Not because it is wrong, but because it may be incomplete. The reason lies in something Einstein himself never fully accepted: the existence of dark energy. In the late 1990s, astronomers studying distant supernova explosions discovered something astonishing. The expansion of the universe was accelerating. Instead of slowing down under gravity, galaxies were moving apart faster over time. To explain this behavior, cosmologists introduced dark energy, a mysterious component that now appears to make up roughly 70% of the universe's total energy. Dark energy behaves like a kind of anti-gravity. It pushes space outward, and its origin remains unknown. Einstein once introduced a mathematical term called the cosmological constant to allow for a static universe. Later, he reportedly called it his greatest mistake after the discovery of cosmic expansion. But modern cosmology has revived the concept. Today, the cosmological constant is one possible explanation for dark energy. Yet even this solution raises questions, because theoretical predictions for the energy of empty space differ from observations by an enormous amount. Some calculations suggest the cosmological constant should be 10 mu square, times larger than what astronomers measure. It is one of the largest discrepancies in all of physics, and this is where Webb's discoveries might connect to a deeper issue. If the early universe formed structures faster than expected, if the expansion rate appears inconsistent, if galaxies and black holes appear earlier than predicted, then perhaps dark energy behaves differently across cosmic history. Some researchers propose the concept of early dark energy. In this idea, dark energy briefly became stronger in the young universe. This temporary boost could accelerate cosmic expansion and alter how structures formed. Later, the energy density would fade, leaving the modern universe dominated by the weaker dark energy we observe today. Such a scenario might help reconcile the Hubble tension, while also allowing galaxies to form earlier. But evidence for early dark energy remains tentative. Another possibility is that dark matter itself interacts with dark energy. If these two mysterious components influence each other, the evolution of cosmic structure could change dramatically. Some models suggest that dark matter particles might decay or transform over time. Others propose new forces operating only within the dark sector. All of these ideas remain speculative, but Webb's observations are giving scientists new data to test them. Because every deep image captured by the James Webb Space Telescope adds another chapter to the cosmic story, and that story may be more complicated than our current theories predict. The universe has surprised humanity many times before, and it may be preparing to do so again. There is a strange paradox at the heart of modern cosmology. The deeper we look into the universe, the further back in time we travel. Light takes time to cross space, so when the James Webb Space Telescope observes a galaxy 13 billion light-years away, the telescope is not seeing that galaxy as it is today. It is seeing it as it was 13 billion years ago. In other words, Webb is watching the early universe unfold, and what it is seeing is beginning to challenge long-held assumptions about how cosmic history unfolded. For decades, cosmologists believed the early universe was relatively simple. The Big Bang created a hot, dense plasma. That plasma cooled. Hydrogen atoms formed. Gravity slowly pulled matter together. The first stars ignited. Galaxies assembled. Everything followed a gradual progression. But Webb's discoveries hint that cosmic evolution may have moved faster than predicted. Galaxies appearing earlier. Black holes growing faster. Structures forming sooner. Each observation alone might be explained, but taken together they suggest something deeper. Perhaps the universe was more efficient at building structure than our models assumed. Or perhaps our models are missing an ingredient. One possibility being explored by physicists involves the behavior of dark matter. Dark matter is believed to make up most of the matter in the universe. It does not emit light, it barely interacts with ordinary matter, but it exerts gravity, and gravity shapes the cosmos. If dark matter particles interact with each other in subtle ways, those interactions could accelerate the collapse of matter in the early universe. Clusters of dark matter might form faster, gas could fall into those gravitational wells more quickly, stars could ignite sooner. Another idea involves something called self-interacting dark matter. In this model, dark matter particles occasionally collide with each other. Those interactions could redistribute energy inside dark matter halos, altering the way galaxies form. This might explain some of Webb's observations of unusually dense early galaxies. But dark matter is not the only mystery. Another key ingredient in the universe's evolution is dark energy. Dark energy appears to drive the accelerating expansion of space, yet its true nature remains unknown. Some scientists suspect dark energy may not have been constant throughout cosmic history. If dark energy behaved differently in the early universe, it could alter the timeline of galaxy formation. It might even help explain the disagreement between different measurements of the Hubble constant. Others are investigating whether the equations derived from Albert Einstein's theory of general relativity require subtle modification on the largest cosmic scales. Such ideas are controversial. Relativity has passed every experimental test so far, but most of those tests occur within galaxies or around compact objects like black holes. The universe itself spans billions of light years, and the behavior of gravity across those distances is still being explored. What Webb is revealing is not necessarily a failure of Einstein's theory. Instead, it may be exposing the limits of our current cosmological models. Models that combine relativity with dark matter and dark energy. If any of those components behaves differently than expected, the timeline of cosmic evolution could shift. And that is exactly what Webb's observations seem to suggest. But there is another reason these discoveries are so important. They remind us that science is not a finished story. Every generation of scientists inherits a model of the universe, and every generation improves it. In the early 1900s, astronomers believed the Milky Way was the entire universe. Then Edwin Hubble showed that countless galaxies existed beyond it. Later discoveries revealed that most of the universe consists of dark matter and dark energy. Now Webb may be revealing that the earliest chapters of cosmic history unfolded differently than expected, and that possibility is both thrilling and humbling, because it means the universe still holds secrets waiting to be uncovered, and the deeper we look, the closer we come to answering one of the greatest questions humanity has ever asked. How did everything begin? There is something extraordinary about the moment humanity realizes its understanding of the universe might be incomplete. It has happened before. In the late 1800s, physicists believed they had nearly finished discovering the laws of nature. Newton's mechanics explained motion. Maxwell's equations explained electricity and magnetism. The universe seemed orderly and predictable. Then cracks began to appear. Experiments involving light and motion produced results that classical physics could not explain. Those puzzles eventually led to the birth of special relativity and quantum mechanics. Suddenly the universe was stranger than anyone had imagined. Space and time could stretch, particles behaved like waves. Reality itself appeared probabilistic. A century later, physics stands at another similar frontier, because while general relativity explains gravity and quantum mechanics explains the microscopic world, the two theories do not fully agree with each other. Physicists have long searched for a deeper theory that unites them, a quantum theory of gravity, and observations of the universe often guide those breakthroughs. For example, the discovery of the cosmic microwave background confirmed the Big Bang model. The detection of gravitational waves confirmed a major prediction of relativity. Each new instrument has revealed a deeper layer of cosmic truth, and now the James Webb Space Telescope may be opening the next chapter, because Webb is not just another telescope, it is a machine built to see the first light in the universe. Its enormous mirror and infrared sensitivity allow it to detect galaxies that formed when the universe was still in its infancy. galaxies whose light has traveled for more than 13 billion years before reaching Earth. When scientists designed Webb decades ago, they hoped it would help answer several key questions. How did the first stars form? When did the first galaxies appear? How quickly did cosmic structure grow? But Webb is doing something else as well. It is revealing the unexpected, galaxies that appear surprisingly mature, black holes that appear surprisingly massive, structures that seem to have emerged faster than predicted. None of these discoveries alone proves that Einstein's theory is wrong, but together they suggest that our current picture of the early universe may be incomplete, and that possibility excites scientists because the greatest breakthroughs often come from anomalies. When data refuses to fit existing theories, researchers must either refine their models or invent new ones. In the coming years, astronomers will gather far more information from Webb. Spectroscopic measurements will confirm distances to early galaxies. Simulations will attempt to reproduce Webb's observations. New telescopes, including next-generation ground observatories, will probe the universe in even greater detail. All of this data will help scientists determine whether the current tension represents a genuine challenge to cosmology or simply a misunderstanding of the earliest galaxy. But one thing is already clear. The early universe was more complex than we imagined, and the deeper we look, the more mysteries appear. Because Webb's observations are not the final word, they are the beginning of a new investigation, one that could reshape our understanding of gravity, dark matter, dark energy, and the formation of cosmic structure, and that investigation is only just beginning. There is a reason astronomers often say that the universe is the ultimate laboratory. On Earth, experiments happen inside controlled environments, particle accelerators, laboratories, observatories. But the cosmos conducts experiments on scales humanity could never recreate. Stars collapsing into black holes, galaxies colliding, matter falling into gravitational wells billions of times stronger than anything we could simulate. These extreme environments allow scientists to test the laws of physics in ways impossible on Earth. And that is precisely why the James Webb Space Telescope is so important, because it allows researchers to observe the universe at a time when those cosmic experiments were just beginning. The earliest galaxies were not quiet places. They were violent, turbulent, filled with rapidly forming stars and powerful radiation. Supernova explosions constantly reshaped their environments. Gas clouds collapsed under gravity. Black holes devoured surrounding matter. Every process in those early galaxies unfolded at incredible speed, and through Webb's infrared vision, astronomers can now witness these events across billions of years of cosmic history. Each observation adds another piece to the puzzle. Each galaxy tells part of the story, but sometimes the most important clues come from the gaps between those pieces, because when observations refuse to align perfectly with theoretical predictions, scientists must reconsider their assumptions. For example, the Lambda-CDM model has been remarkably successful in explaining the large-scale structure of the universe. It predicts how galaxies cluster, how cosmic filaments form, how matter flows through the cosmic web. And in most cases, the model matches observations beautifully. But Webb's discoveries may be revealing details the model did not fully anticipate. Perhaps early galaxies formed stars more efficiently. Perhaps gas cooled faster in primordial environments. Perhaps the first stars were even more massive than predicted, or perhaps dark matter behaved differently than expected under certain conditions. Each of these possibilities is being explored by astrophysicists around the world. New simulations are already incorporating Webb's observations. Researchers are adjusting parameters, testing alternative scenarios, examining whether small changes in early conditions could produce the galaxies Webb is seeing. Because cosmology is not static, it evolves with every new dataset, and Webb's datasets are enormous. Each deep field image contains thousands of galaxies. Many of them are extremely distant. Their light began traveling toward Earth when the universe was only a few 100 million years old. Those ancient photons carry information about the earliest structures in the cosmos, information that may help scientists answer one of the most profound questions in physics. Is our current understanding of gravity complete? For more than a century, Albert Einstein's theory of general relativity has served as the foundation of cosmology. It describes how space-time curves in response to mass and energy. It explains the motion of planets, the behavior of black holes, and the expansion of the universe, and every experimental test so far has confirmed its predictions with remarkable accuracy. But even Einstein suspected that deeper layers of reality remained hidden. He spent the final decades of his life searching for a unified theory of physics, one that could connect gravity with the forces governing atoms and particles. That quest continues today, and sometimes the universe itself provides hints, unexpected observations, anomalies, patterns that do not fit neatly within existing models. Webb's discoveries may represent exactly that kind of hint. Not proof that Einstein was wrong, but evidence that the universe may contain additional layers of complexity, layers that scientists are only beginning to uncover. And the more we observe, the more fascinating the story becomes. Because every galaxy Webb detects is not just a distant object, it is a message from the past, a signal from the earliest chapters of cosmic history, a reminder that the universe has been evolving for billions of years, and that humanity is only just beginning to understand its story. For most of human history, the universe appeared simple. The stars rose and set. The planets moved across the sky. Night after night, the cosmos seemed calm, predictable, eternal. But every time humanity built a more powerful instrument, that illusion shattered. The invention of the telescope revealed that the Milky Way was not the entire universe. The discovery of cosmic expansion showed that space itself was stretching. The detection of dark matter revealed that most of the universe is invisible. And the discovery of dark energy demonstrated that cosmic expansion is accelerating. Each discovery forced scientists to rethink their understanding of reality. Now, the James Webb Space Telescope may be revealing the next chapter, because Webb is showing us the universe during its earliest moments of structure formation, when the first galaxies were emerging, when the first stars were igniting, when the first supermassive black hole seeds were beginning to grow. And what Webb is seeing may be slightly different from what cosmologists expected. Galaxies appearing earlier, structures forming faster, black holes growing more rapidly. None of these observations alone overturn existing physics, but together they suggest that our picture of the early universe may need refinement. Perhaps the first stars were larger than predicted. Perhaps dark matter collapsed more efficiently. Perhaps gas cooled faster in primordial galaxies. Or perhaps the expansion history of the universe was slightly different during its earliest epochs. Each of these possibilities is now being investigated. New observations are arriving constantly. Astronomers are measuring the chemical composition of early galaxies, mapping the distribution of matter, studying the environments around ancient black holes. Every new dataset helps scientists test competing explanations, but what makes this moment in cosmology so exciting is the possibility that Webb could reveal something entirely unexpected. Because history shows that the universe often surprises us. When Albert Einstein developed general relativity, he was trying to solve a problem involving the motion of Mercury. He did not expect his equations to predict black holes or gravitational waves. Those discoveries came decades later. Similarly, the observations being made today may lead to insights that scientists cannot yet foresee. Perhaps the current cosmological model will survive intact, with only minor adjustments. Perhaps new physics will emerge to explain the earliest galaxies. Or perhaps Webb will uncover entirely new phenomena that force us to rethink how the universe began. And that uncertainty is the essence of science, because every discovery opens the door to deeper questions. What is dark matter? What is dark energy? How did the first galaxies form? How did the earliest black holes grow so large so quickly? And could there be aspects of gravity we have not yet fully understood? These questions are no longer purely theoretical. For the first time in history, humanity has the technology to observe the universe at the moment when those processes began. The light reaching Webb today began its journey billions of years ago, long before Earth formed, long before the Sun existed, long before life appeared on our planet. Those ancient photons carry the story of the universe's birth and evolution, and every time Webb captures a new image, that story becomes clearer, but it also becomes more mysterious. Because the deeper we look into the cosmos, the more we realize how much remains unknown, and perhaps that is the most profound lesson of all. For more than a century, Einstein's vision of gravity has helped humanity understand the universe. but the universe itself may still hold surprises even Einstein could not have imagined. And somewhere in the faint glow of those distant galaxies, the next great discovery may already be waiting.